Achim Menges is a registered architect and professor at the University of Stuttgart, where he is the founding director of the Institute for Computational Design and Construction since 2008. He has also been visiting professor in architecture at Harvard University's Graduate School of Design from 2009 to 2015. His practice and research focuses on the development of integral design processes at the intersection of morphogenetic design computation, biomimetic engineering, and computer-aided manufacturing that enables a highly articulated, performative built environment.
Thanks a lot for the introduction, and especially thanks a lot for the invitation. It's a great pleasure to be here. Fantastic event, fantastic country. So I'm really enjoying it a lot. What I will talk about is primarily the title is Integrative Computational Design and Construction, which is the title of our Cluster of Excellence. And what I'm really going to talk about is the notion of co-design and what a new kind of co-designer that we may have will be in the future. So this is really the main theme I would like to entertain. And of course, I fully understand there would be many ways of how one could actually, coming from Stuttgart, how one could actually give a talk about the relation between Uruguay and what has happened in the 20th century in terms of lightweight structures at the University of Stuttgart. But I did consciously decide not to do this explicitly. But you will see that there are some repetitive themes that come up, and maybe we can discuss that at the very end. So I'm a absolutely great admirer of Eladio Diester's work. Also super happy to have been able to see some of it already on this trip here. And I think if there is a high level of integration of design and construction, it's right there, no? And I will come back to this. But I decided to talk about something else, and this is how we may have to rethink our relationship to digital technologies. Maybe also in this kind of interesting line of keynote speakers that we already had. And to begin sort of engaging with this sort of argument, I may go back to one of the quotes that I used at the beginning of my academic career a lot, which is from Kostas Tersidis, which talks about the difference of computerization and computation. And I think it's actually quite remarkable that I think this quote is from 2006. We still need to have this argument, because I think there's there's still a lack of really deep understanding of what digital technologies actually may have to bring to may bring to the table in architecture. So I think, of course, there's one aspect to digital technologies that you can use them as an extension of what we already know. So it's kind of a next step in a linear process of, I would say, evolving technologies. And I think this typically ends up in a situation that you may say you computerize what has already been there in terms of methods and processes. So I think it's nicely captured here by saying computerization is about automation, mechanization, digitization, and conversion. Generally, it just involves the digitization of entities or processes that are preconceived, predetermined, and well-defined. So I think what I tended 20 years ago, tell my students, it's basically Microsoft Word. It's the equivalent, the digitalization of the typewriter. It's just that you change a piece of paper to the screen and the mechanical keyboard to your digital keyboard. It doesn't change your conceptualization of writing at all. It just computerizes it, makes it a bit more effective, because you don't have to deal with paper, you can edit it very quickly. Of course, this is now beginning to be challenged, and I think it's interesting to go back to this quote, because Tersidis goes on and says, in contrast, computation is about the exploration of indeterminate, vague, unclear, and ill-defined processes. Because of its exploratory nature, computation aims at extending the human intellect. I mean, surely the right image is about computation. I'm not entirely sure what it's about extending the human intellect, honestly. But that's actually, I think, what we want to maybe discover in the next 45 minutes. Because I think it's absolutely important that we find a way of not just, I think, understanding what is happening around us, but to find a position as architects and designers in this kind of emerging world. And I think if we're really honest, we are still at this sort of stage where we basically are deeply rooted in a pre-digital world, no? I think whenever we apply or whenever we employ digital technologies, also actually the AI-driven ones, we are basically still thinking about a process chain that is based on pre-digital approaches. And that means we basically have digital methods, and I include here AI voice-driven BIM modeling, that is for pre-digital building design. All the conventions of pre-digital design are still there and are actually embedded in all the classes that you deal with, all the classes that the AI knows. It's actually I would say it's essentially pre-digital. Same, of course, applies to automated fabrication, robotic production. It all typically revolves about the automated fabrication of essentially pre-digital building systems. So I think there's sort of very fast development that also Neil alluded to in his talk of computational technologies begins to widen that gap between the pre-digital physical world and the computational world that is beyond the grasp of most of us. So what would be a way to deal with this? And I think we have tried to identify an overarching methodology that positions, let's say, the real potential of digital technologies in a slightly different way. So instead of computerization, we try to use computation primarily to enable the integration of, on the one hand, of course, the computation design and engineering methods, the cyber-physical robotic fabrication and construction processes, and especially, now T got lost, the truly digital material building systems. That's what we are typically missing, no? So what does it actually mean in terms of on the physical side, if you have this incredible computational power? And I think how we like to refer to that is that it's all about the co-design of methods, processes, and systems. So it's really the co-design and I know that there are many different ways of how you can define co-design. It's not a participatory process, as you know from social science or participatory processes, but it's actually the way how computer science hypotheses use the term co-design. So it's a co-design as an integrative and interdisciplinary methodology. And I think the interesting thing is that it opens up the possibility to think about the potential of artificial intelligence as a co-design. Yeah. So in my eyes, it's not about human versus machine. It's not about trying to beat AI by playing chess. It's about playing together and going places that you could not go by yourself, both agents. So I think this idea of AI as a co-designer or AI as a co-pilot, I think is interesting, and I think this methodology opens up possibilities to engage with those digital technologies in a way that they also begin to really alter the physical domain. not just the digital. So we have been exploring this for a long time across many different projects, and I would just use this talk to explain a couple or present a couple of more tangible projects and how this notion of co-design has been instrumental in the development of them. I should also say that there is a side situation to that where we, at the very beginning, and as we're still doing, of course have another model for a really high level of integration, and that's living nature. No? So there, everything is embedded. Information, form, performance. I will not talk about this either. It's another lecture. So, but I think it is important to recognize that this has been there and has also been tried. So, well, being here, I thought one appropriate first example would be to talk about shells and talk about the notion of co-design in the context of how you can actually develop methods, processes, and ultimately a genuinely digital architectural system, the segmented timber shells, through the feedback of and the reciprocal effects of those aspects on each other. So this is a work that we have been doing for almost 10 years now. And I will try to sort of summarize it a little bit along this pavilion that we completed in 2019 for the Bundesgartenschau in Heilbronn. So this is a timber shell, and it was used as a kind of multi-purpose event space. Covers around 600 square meters. The central shell has around 500 square meters and has a free span of 30 meters. So it's quite a high performance structure, I would say, for a timber system. And I think the interesting thing about these timber shells is that they work like a three-dimensional puzzle in space, and they do work as, I think, an architectural surface as well as a structure. And because of the let's say, specific differentiation of all the elements that make up the segments. So the idea here is that you actually capitalize on the possibility to differentiate every element, every joint through the robotic production, and by that you actually inject a new life into kind of shell structures, because you are addressing some of the main issues with current or with previous shell construction, which, for example, has to do with the fact that you usually have to build a shell twice, once as a false work and once again as the actual structure. That's not necessary here. So I think it's also interesting because the shell structures are a vehicle to question current, I would say, economies of means in architecture and construction. So I think we are experiencing an acute, of course, environmental crisis in architecture, because we have been used, or we have adopted a paradigm of creating the built environment that buys actually less design and construction effort by an incredibly high investment into materials and energy. So this is somewhat the opposite here. So here we actually complexify, you may say, construction to have a higher investment on the intellectual side in regards to design and construction. And for that, we use a lot less material. So for example, the shell segments are all not sort of just one element, as you would expect, but the shell segments are consisting out of many different elements, as you can see here. So that's one of those hollow segments that has an upper plate and a lower plate and a ring beam, and all of them contribute to this idea that you can actually enhance the way we relate to the resources we have by adding design effort. And I think the interesting thing is that in the co-design offers a possibility to, let's say, afford this because you can deal with all the complexities that come with it. So for this, we have actually developed an agent-based modeling framework. It exists in many instantations. We have this also now as a completely open source software that everyone can actually use. And we have one module for those segmented shells that allows for a direct feedback with structural modeling, of course, but also with fabrication modeling. And honestly, what we're looking at here is just a geometric representation of it. We don't need that. It's just there because we're still used to this sort of geometric notational formats. It's not really required. It would be difficult to just show you the code. But I think what is the really interesting part here is that together with the actual building system and this particular architecture, the process of how it's going to be materialized is co-designed. So it's not just sort of taking the constraints from an existing project, and existing process is not designed for manufacturing, it's actually co-designing the fabrication unit and the related processes together with the building system. So in this case, this happens by actually defining what are the tasks and what are the skills that you need to have in order to manufacture those segments. And then you actually begin to have a kind of task skill matching system, which is actually something that can very nicely communicate to AI, for example. We'll come back to this later. Here, the aim was to say, okay, the only way we can ever do this, and I think what is also important to mention is these projects happen on an incredibly tight timeline and with extremely tight budgets. So you just have to imagine from the start of the project, and literally the start of the project, until the opening of this event was 13 months. So all the research had to happen, and all the building had to be constructed, designed, constructed, and actually certified by the German authorities within the 13 months. And sorry, there's no way you can delay this because it's an event where 2 million people attend, so you cannot say, okay, we'll do the opening next week. So this idea of co-design, I think, is ultimately leading to this multi-scale, multi-agent system where each building element has its own behavior and it can learn how to actually adjust to the multiple constraints that it has. Structural, geometric, life cycle analysis. And I think, again, actually the representation is just there for us to understand it honestly. The agent system doesn't need that, but I think for us it's good to look at geometry especially, and I think that's the big advantage to this kind of AI systems. This is interactive, so you can intervene with the system, kind of a gray box AI. No? So you can actually grab an agent, you can move it around, and everything around the segment that you move actually recomputes following the kind of self-learning agent system, following the multiple scales from the segment all the way down to every last nut and bolt. So I think it's also here, I would say, you have an AI co-designer. No? Takes care of the complexities that you simply cannot process with our cerebral system. But it also allows you to go to places in regards to design that you could not go without that co-pilot. I think one other aspect that is very interesting about this idea of co-design is that you begin to question, I would say, typical models of building delivery. And I would say the economic models that go with it. So here we have this co-designed mobile unit. You can bring it to any manufacturer. You can actually include it in the tendering process. So in the best sort of Marxist version, you have delineated the means of production from the capital. And I think that would be very interesting models, let's say socioeconomic models of how you could actually think about construction in a very different way, using these small, agile mini factories that could be so for example, embedded in kind of unionized systems. So this thing, this is actually the slide, so you can just ship it anywhere. Is not dependent on existing industry structures. In the end, we brought it to one timber manufacturer that we teamed up with, and there, in its unfolded state, actually produces the elements in this project in a fully automated manner. So I will walk you through this for the second cassette. Starts off by picking the bottom plate, mounts it on the rotational table of the robot, and it applies the glue, that is the structural glue bond, and then it fixes the ring beams actually with timber nails, so that it remains to be a completely monomaterial system. There's not a single piece of steel in this structure. Applies the glue on the top, applies the timber nails as well, then goes out, goes into a press, and comes back. It takes around 7 minutes to build one of those elements. And that's the only way you can do this in this timeline, and with the, let's say, time and financial means that were available. And that's not really the key point. The key point is that, and this is where we sort of shift towards sort of this realm of genuinely digital building systems, is that of course you have a level of accuracy of these force and form-fitting joints, which is around 0.3 of a millimeter, that actually allows you to build the full shell, 30-meter shell, without needing any force work, like a three-dimensional puzzle in space. The whole thing was actually built by 2 craftsmen in 9 days. So it's actually a very cheap structure, both from a kind of ecological and an economic point of investment. Of course, it also has a different concept in terms of dealing with tolerances, for example. This is the last keystone element. If you put this in, it doesn't fit, you're in trouble now. You have to go back and start from scratch. Here, actually, it worked. I would say the result is a very authentic piece of architecture in many ways, because the only thing you see is this sort of expression of the timber segments being illuminated, having the kind of hollow spaces illuminated that you need to actually assemble the shell, which are bolted together. So I think it also sort of, from that point of view, it opens the door to investigating and discovering new kinds of architecture that are actually driven through the physicality of the dimensional piece, rather than, I would say, some sort of inspirational image. I think the inspiration runs much deeper, no? It's kind of you enter on a completely different level with the computational power, because you intervene directly with the potentials of materiality and materialization. Of course, I think it's also a nice proof to the hypothesis that with more form you can have less material. But I think the interesting thing is that it's not just, I would say, something that you can experience on a qualitative level, but something that you can also explain on a quantitative level, which sometimes is completely lacking from our kinds of discourse. So we have a span that spans 30 meters and it has only 160 millimeter depth. It's actually really shallow for a long span timber shell, and it weighs only 38 kilograms per square meter. So the resources you invest are minimal, which I think is a kind of a discourse we cannot shy away from. I think for too long we have sort of disentangled the cultural from the ecological. I think now ecological is cultural. So I think we also have to be quite serious about these things. No? Good. I think the experiential is also interesting. And I think this thing was so popular that it was actually visited by 2 million people during the time it was there. At the beginning, actually, the client was super worried about the acoustics. Because, of course, a lightweight shell, this is kind of concave, so the worst when it comes to conventional understanding of acoustics. It had perfect acoustics. They were doing TV shows in there, because it also questions this idea of mass as being the only way of how you control acoustics. Here, I think this works like an old Persian music chamber, like the music chamber in Isfahan, where you basically control reverberation times by geometry rather than by material absorption. So I think that was actually a discovery for us. That wasn't planned, honestly, but it was amazing to see. It's actually a principle that we now use quite often. I think what is also very important to say is that this building was from the beginning designed to be circular. So not only being monomaterial or reusing certain elements, no, the whole shell, because it was clear from the beginning it's kind of temporary building. And you can imagine that there were some people that doubted that you can, well, even if you manage to put the three-dimensional puzzle together, that you can take it apart and sort of rebuild it somewhere else. In the end, it took 10 minutes actually to take the top piece out with some hydraulic stamps. So you can dismantle the whole shell. The shell is actually bolted, not screwed. So not a single piece was actually damaged. And we rebuilt it for the next Bundesgartenschau in Mannheim, which you can see here on the right. And after this has just finished, and now it will move on and will become a closed building as an auditorium space for a university in south of Germany. So it's kind of already in its third life, which I think is also quite interesting. It will also have another life because this was the segmented shells. Is now something that we finally managed to get to a point, develop to a point within 10 years that they're really competitive. So we're building this building here for our Cluster of Excellence, which is both the biggest research project we have and ultimately the home of our cluster. So all the 150 people will actually be researching there. And the entire roof, which is around 3,500 square meters, is built as a segmented timber shell. That shows, I think, that if you take those opportunities serious, and if you're serious about this co-design methodology, within a relatively short time, you can basically innovate on a level that is actually competitive, because you can imagine that no public university is willing to spend more than what is really necessary to cover the space that they have. That's just a sideline. We did another small project that I wanted to show you, which was really interesting for us because we began to question some of those aspects preparing for this big building, which is this Liftmat's shell here, which is at the FIT Center for Interactive Materials and Bio-Inspired Technologies at the University of Freiburg. So it's sort of a satellite building to the main building that you see here on the right, that the natural scientists use as what they call an ideas laboratory. So they need a space where they can get inspired, natural scientists, you can imagine that. And they can't get inspired in the gray box next to it. So they want to have this as a sort of multi-purpose situation, which was a perfect opportunity for us to actually think about the additional, let's say, I would say, advancements that we needed to make in order to get this kind of segmented single shell system ready to be used for a permanent building, used all the year round, needing to fulfill all the requirements of the German building code, not only when it comes to structure, but also installation, embodied energy, everything. So, and I think what was interesting for us here is that we were really able to question some of our initial preconceptions about, or conception about how a segmented shell should work. First, of course, we extended the multi-agent system to include all other building systems as well. So it's not just the main load-bearing structure, but everything, even the buttons that are controlled according to the water flow and all this. And we did so by really absolutely maximizing the use of bio-based materials. So here everything is bio-based, except the water barrier. That's the only thing that we can still need to use synthetic materials, but it's not glued or anything. It's sort of just applied, so you can take that off if you want. This is here, sort of. But one aspect that was really interesting is that we also extended this idea of co-designing the fabrication platform with it. And what we were really interested here was to see, okay, if we have this sort of agent system that can assign actually tasks, and then you have matching skills, why don't we actually integrate, rather than going for a fully automated process, why don't we integrate human skills here more intensely? So now we have this sort of what we like to call a multi-actor fabrication approach, where you can, on the fly, assign the tasks to humans and robots, and they interact together, and actually they can learn from each other. To the point that actually this human-robot collaborative approach turned out to be 75% faster than the fully automated approach. Also kind of counterintuitive. Anyways, that of course involves a lot of mixed reality. You'll see in a second. So there is a part that is fully automated. That's what the robot can do pretty well. It's this time actually we only have one robot, and it lays out 4 elements in the line, which allows one to actually have shared workspaces. And then there are other tasks like the integration of the lights, the acoustic elements, where of course the humans are super good with their skill sets to contribute. And I think it's sort of within that shared workspace that this fabrication here unfolds. So it's really no longer about full automation, but it's how do you take care of the autonomy of both the human and the machine. So here we also, I think I forgot to say this, we work with a lot simpler materials. So we no longer use the highly engineered wood products, but it's really simple. Just the rim beam, for example, is just raw cut timber. And then we also thought, okay, how can we also use the same idea and now also integrate construction into the co-design approach? So how would this element actually look like if it wants to be assembled by a robot rather than by humans? And that meant, for example, the complicated finger joints are not really suitable. Just as one example, so we developed this, actually this is something that the systems engineers primarily did in 2 approaches. So we have 2 run-off-the-shelf, sort of just off-the-shelf spider grains, but they're equipped with a control unit that allows them to actually assemble the building autonomously. And there are 2 ways of controlling them. One is by a couple of robot total stations, and the other one is actually just having AI practicing the thing. In the end, the AI actually works a lot better than the typical stations, trying to go for an old model of accuracy rather than actually being capable of adjusting on the fly. So the way that this actually works out is you can see this here. So the two robots collaborate. One is actually placing the segment, and the other one has a screwing effector, and it's sort of screwing the pieces together. So it's the collaboration between these two units. Here, again, we are in this kind of fully automated paradigm. I think there's a lot of scope for also seeing, of course, the human in this. So the robot, as I said, is placing units, and then it finds actually the screw holes, and then it puts the screw holes in when it has properly positioned the elements and measures them. So I think, of course, the system lends itself to this because it's very lightweight. I mean, cannot do this with a concrete slab, of course, but because it's so lightweight and also small elements, that it really works. In the end, I think it really creates, sort of pushes this segmented timber shells towards another, I think, spatial expression. I think here it was really about how this element sits on this open campus. It's kind of unconstrained. It really has this flowing space towards the outside. And at the same time, it was also meant to be a proof of the hypothesis that this co-design methodology can really reduce economic impact. And for that, we did a very, very thorough study on the life cycle analysis, including all the data that had to be actually derived for the manufacturing process and everything. Turns out that this building has 63% less global warming potential compared to a conventional timber building. And not a conventional building, steel or concrete, but a conventional timber building. And I think that's important. I think it's also important because it shows that there is no, I would say, we kind of tend to entertain this dialectic between what is effective and what is expressive. I think there's an interesting, different dialogue that one can enter through this co-design methodology. One thing that is also really important is, of course, we tend to focus a lot on, let's say, the actual fabrication construction. Here, for this building, we of course had also to think about how will this actually work during its lifetime. And as you may notice, there's no building services in this building, but it needs to work all the year round. Freiburg does not have a super harsh climate, but it's kind of in Germany. So, and all the building services are actually in this black box. So the whole building is actually the indoor comfort is generated by an activated slab, which is actually made from recycled concrete. This is the first recycled concrete activated slab in Germany. So you have water flowing through the concrete, which is actually going through, it's taken from a local source. Maximum temperature is around 25 degrees. And then we actually have this skylight that you see here, which is this kind of prominent feature, which you call the energy gate, which actually allows the building to be heated by the solar load during the winter. And the interesting thing about this is this happens without any supply of external energy. So this was the first time that we were able to implement our adaptive building skins that we have been developing for a long time in a real project. And what is important to notice is that so you have these self-adjusting, materially programmed elements, and they're sitting in this hollow box window, which is actually in front of the insulating window. So it's really just modulating the UV light entering an infrared light entering the building. So I think it's another example of how co-design can actually work on a very different level, namely on how you design the material structure, which is something, and here I have to refer to this biological example, is something that is foreign to us in our discipline. We don't program materials. Actually, we invest the vast amount of energy and cause most of the missions by trying to homogenize our materials through high energy processes, which is of course exactly the opposite of what nature does. So here you have a nice natural example of material programming. It's a spruce cone, not very familiar maybe here, or you may have pine cones. Spruce cone is very common in Central Europe. And the interesting thing about the spruce cone is it grows on the tree in a wet state, and then the scales just open by themselves with the wooden material of the scales drying out. So basically what it does, it translates a dimensional change of the cellulosic material into a shape change of the element. And it's interesting, no? Because it's sort of, the material is not only the sensor, but it's also the motor and the regulating entity. So all the agencies in the material. So this is something we have been working on for also 10 years now, analyzing very carefully the internal structure of the pine cones. And then initially we actually worked with just timber veneer, extracting the material information from it by scanning every veneer piece, and then programming the sequential motion into it, as you can see here, as we did for the fractal laying, which is of course not a very robust way of doing it, and it doesn't allow you to actually design other kinds of movements than those typical bilayer systems. So we've now worked a lot on how we actually can dismantle the timber into lignin, hemicellulose and cellulose, and then actually print it together to actually expand the catalog of kinematic mechanisms that we can design through the material agency in a manner. So here, this is sort of the benchmark, same mechanism, and you can see how it responds just to a change of relative humidity. So there's no motor, no electricity, nothing. No? It's just the ambient environment changes, the relative humidity level in the environment changes, and then it opens and closes. And that's the physical stimulus that we use in the box window, and that's why the window works at any temperature. So if temperature would be the stimulus, it would work in winter or in summer, but it would not work in all seasons. But relative humidity always changes based on the temperature differential. So that's why here we just control actually the solar light hitting the box window, and then the air volume in the window heats up, which means the relative humidity drops, which means that the thing closes. And you can also override that because there are a couple of small valves that you can actually control, and actually the valves are also controlled through a sophisticated mechanism. So that's the only thing that you can actually use in order to have not only a completely passive system, but a kind of system that can have occasionally adaptive stimulus. So here you can see that kind of the sun comes up. Before the sun comes around, the windows thing closes entirely by itself. Then during daytime, it kind of effectively shades the system. Sun disappears and the system opens again. No energy, no mechatronics, no nothing. Just capitalizing of what the material has anyways already. Good, and I think the interesting thing is that this kind of idea of material programming also works on a large scale. So initially, when we were always doing this kind of timber veneer stuff, everyone said, yeah, but, you know, we're dealing with architecture, so these things need to be big. Maybe that's a very old white man attitude to things. In any case, I think for all these adaptive mechanisms, of course you need to scale them, but you don't scale them by size. I mean, the shading system, you scale them by number. So I think the units would need to become smaller in order to be really scalable. But it's interesting that the same phenomenon also works for timber. And I think here we're beginning to enter a situation where we can say, okay, we can use this idea of more form combined with less effort in shaping. And we can really question how we typically think about how we superimpose our will on the pieces of timber, basically through brute mechanical force, as you can see here on the left. No? That's glulam production. You invest a hell lot of energy in trying to force the timber in doing what you designed. Of course, it's a very different conversation if you enter into a dialogue with the material itself. And we all know that timber has that capacity because we have textbooks that tell us how to avoid these things from happening. This is actually from a timber textbook that uses this example as a defect. So please avoid timber to bow, carp, twist, anything. No? And I think computation allows us to have a very different way of engaging with these capacities that are innate in the material anatomy. And I think the interesting thing is that it really works also on large scale. So this is a piece of timber that is about 1.5 meters long and 40 millimeters thick. And you can literally program the shaping of the timber in the reduction of the wood moisture content from 22% to 12% into the piece. And then it becomes more a question of how can you integrate that? How can you co-design with this material behavior so that you are able to actually have this dialogue with the material in the design process. And for that, of course, computation again is very interesting. Initially relied a lot on the, let's say, I would say classical approach on having analytical models, modeling the material behavior. Now we have actually changed to data-driven models because we have a couple of projects where we produce this self-shaped timber in large quantities. And that means we can actually have very, very fast, very agile predictions based on the specific anatomy and wood moisture content. So here I think it's also an interesting way of an alternative use of artificial intelligence as an enabler to have this conversation. In any case, I wanted to show you the project that demonstrates how this works on a larger scale. We were able to test this in the Urbach Tower, just in the south of Germany. It's kind of a mainly meant to be actually a landmark in this really beautiful landscape, so that there are several of those landmarks that connect along a valley, so that visitors actually find an interesting way to navigate through that space. And of course, I think what is interesting is if you want to design with the material, you need to have completely different set of design methods to do this. As I said, it's all driven, at that point, it's driven by analytical models. And you're, of course, beginning to intervene with typical ways of how wood is processed. So it's interesting that actually everything that was required to achieve this self-shaping is available in sawmills already. That was actually the main challenge. How do you can integrate the self-shaping in your design process only using the parameters that you can ultimately tweak through the sorting that is already existing in the sawmill. Because, of course, in every sawmill, they scan the wood, they sort it, they have a very good understanding of the differential moisture contents. And then it is about the production of those bilayers. putting them into the oven with tons of other timber material, which of course was here absolutely required. And then in the drying process, you get this shape. Unfortunately, it was impossible to actually capture that in the oven. We're now having another project. We're trying to actually really set up a very sophisticated way of having a camera that can survive the humidity and temperature cycles, so that we don't longer rely on this. But this is what comes out. Sort of the 14-meter long, self-shaped timber pieces, which are actually self-shaped as bilayer packages. And then you have two bilayers laminated on each other, and then a last layer, which is the locking layer, which freezes the shape. So it's a non-reversible situation. So you have to know what the kind of moisture content is that the timber will equalize in its service condition. And I think what's really interesting is that the whole thing was actually prefabricated with our industry partner here in Switzerland, and then the tower was actually delivered to site in 4 quarters and set up in half a day. And here you can see how super thin the actual structure of the tower is, because of course the 3-dimensional corrugation of the complex shape is what contributes primarily to it being actually a form-active structure. So I think it's a very interesting and fitting somehow, because you use a local material, but you sort of find a different way of engaging with it. I mean, this is all done from very local timber here. Find a very different way of engaging with it through, I think, the computational possibilities that we have. But I think it's also important to say that it, of course, changes entirely your conception of how and what you design. I think it sits in this beautiful landscape, and you have this interesting contrast between the concave outer panels and the convex inner panels, which means on the outside there's almost this crystalline shape. On the inside is almost like this timber textile that opens like a curtain and puts the stunning landscape at center stage. And I think it's also quite interesting in a sense that it's really a genuinely digital, or I would say genuinely computational approach to timber, but it only uses the capabilities and potentials that have been in the material already. So I think it really shows how we can engage on a much deeper level with the material, and I think that's very often the missing, I would say, component in the conversations that we enter when we talk about, for example, artificial intelligence. No? That is really enabling a different kind of conversation, a different kind of co-agency between materiality, materialization, and design. So to wake you up a bit, I have a little video that summarizes that project. Okay, I think I will, in the last few minutes of the lecture, I will also like to show you how I think the same methodology works for a completely different material. If you have now sort of investigated how, I would say, co-design can allow you to inject an entire new, I would say, horizon of possibilities into one of the oldest construction materials we have. And now we're changing to probably a construction material that's not even a construction material yet, which are fibrous materials. And we started with the carbon fiber. So I think those are materials that challenge our conception of building and architecture and tectonics fundamentally, because you have a material that is super pliable, very soft, but once it's actually cured, it's stronger and stiffer than steel. Material that comes as a kind of filament, a material where actually 1 kilometer weighs 1 kilogram. So, very different way of thinking about building. And I think, funnily enough, we had the opportunity to investigate that sort of vis-a-vis the timber pavilion at the other end of this sort of central and really cool, expressive landscape of the Bundesgartenschau. We had the chance to build this fiber pavilion, which is sort of exact opposite, is sort of this transparent event space, actually exhibition space for a central exhibit that we didn't design, that was actually given to us to have visitors being able to experience this in a sort of enclosed yet completely visually transparent space. So I think here, of course, the interesting aspect is that what we really wanted to investigate is how we can lend the carbon fibers agency in the design process by not using them as typically on a mold, by actually forcing them into a shape, as we do if we use them for yachts or Formula One cars or whatever, but how we can actually unfold the fibrous tectonic itself. And we did this by having actually just a loose frame, and then you basically have the robot lay the fibers around only a few anchor points. And then in this process of the fibers being wound around those anchor points, the shape of the element emerges as the equilibrium state of all fibers. So it's also only there at the very end of the process. Very counterintuitive, but of course interesting thing is that here you keep the integrity of the fibers. They're continuous. You could actually go back and unwind the whole thing and would end up with one fiber on one spool. And you have zero waste. So what we do is we generate the shape of the structure by this fibrous interaction, and then we lay on those kind of fibrous network another network of carbon fibers, which ultimately is actually the structure. So it's those kind of two fibrous systems interacting with each other and generating in the production process the actual load-bearing structure element. So here you can see this. So there's several fiber rovings, how they are called, running in parallel and synthesized at the top, and you have the robot unit that is co-designed with the element to actually generate this equilibrium state that is then sort of the surface on which or the net on which the carbon fiber is laid. Of course, at the end you take this center core out and you can reuse it for the next element, and you have this bone-like system. And I think here again, of course, it's it's something that is actually beyond analytical modeling, quite honestly. We've tried that many times. Once you actually have a model of a fiber net, what we call a syntax, you can actually analyze it and you can do a fabrication simulation. But to actually come up with a fiber syntax, so sort of the logic of the fibrous net, is something that is very, very interesting to think of as a fiber agent system where the fibers actually learn how to interact. So that's something we have implemented now. It's also very interesting that you need to have completely different ways of accessing that complexity. So while we are developing the AI-driven agent system, we're also developing visual analytics methods which actually computer scientists that allow us to understand how you can actually find performative patterns in this generative process. And of course, I think this is necessary because here you can no longer disentangle what is actually design, what is form, what is structure, what is material, what is fabrication. All needs to be literally co-designed. Especially because, of course, those are building systems that are so novel that they have to, in the end, also deliver on the performance to actually using them in a public building, which the pavilion is. So what we don't talk about very often, but I think you have to imagine all these systems need to be certified, need to go through rigorous performance testing. So there's a hypothesis that needs to be proven and ideally proven positively. So here you can see one of those fiber elements. It's about 5 meters high, needed to be tested 3 times destructively, according to the proof engineer, to the design load, with a safety factor of 4. So it could actually be 4 times thinner, or slimmer, I should say. The thing weighs around 80 kilograms and needs to take 25 tons, 250 kilonewtons in compression. This project was also done in the 13 months timeline, parallel to the timber project. Managed to do this, but I think that's not the point. The point is that you really begin to access design space that is sort of beyond what you can sort of usually derive in a, I would say, with the established design methods and I would say design method systems delivery chains. So I think what is also quite interesting is that all the visitors that came to this building probably have never seen something like this before, had a kind of intuitive understanding of what is going on. Huh? They get the sense that it's kind of fibers and probably the dark fibers are contributing structurally while the white fibers are primarily there for the shape. I think in the end it is an incredibly transparent building, but it's also a building that sort of alludes to this new kind of generally building systems that were impossible to design, engineer, fabricate, maybe even to think of 10 years ago. One fascinating aspect is, of course, that you're also building with material that can actually conduct light, glass fibers. You have this radical transformation between the daylight situation and the night situation. And I think it makes this not only, I think, a technological advancement, but also a spatial experience. Again, I think it's interesting that there's also a quantifiable achievement. You have to imagine that the whole structure only weighs 7.6 kilograms per square meter. That's a completely different ballgame in terms of lightweightness. Also, in Germany, there's a classification. And you're allowed to call your building lightweight structure if it's less than 50 kilograms per square meter. So here we're almost sort of 8 times lighter than this. In any case, I think it's also clear how this sort of dialogue begins to open up architecture possibilities. And then it's also interesting that, of course, the same methodology also works for, I would say, more standard building typologies. I didn't show this for the timber. We're also developing a multi-story timber system. But here, when we were invited by the curator of the Venice Biennale in 2021, where it was sort of the theme was, of course, how will we live together? He asked us to sort of have a kind of projection of what kind of model we would like to envision as a different way of how we may construct the world in the future. And so I think the most in modest terms, we thought, okay, what was the model of the 20th century, which was never really built. So I think it's really important to understand this is not a proposal, it's just a model, and it's kind of our model was full scale, which I think addresses this radical dematerialization that we need to have if you want to get to some level of decoupling of well-being and environmental impact. So I think this was really interesting because it's kind of was a really perfect test case of what does that actually mean if you want to design a building with inhabitable floors just made from fibers. Yeah. So again, here's no steel, no nothing, just fibers and very thin timber plates, and together they actually work as the structural elements, and you have to deal with the complexities of understanding the behavior of every single centimeter of fiber of the fiber network, which is more than 150 kilometers. So there you are happy if you have a co-pilot that can guide you a bit on the way and allow you to actually explore again a design space that was sort of typically beyond the spaces that are approaching for us. So here's actually, initially we thought, okay, that's going to be easy, it's an art piece, no? No. It was considered to be an exhibition space, it had to be engineered according to Italian building code, which we figured is stricter than the German building code, so it's 400 kilograms per square meter. So it was quite interesting. Managed to do this, but I think the real point is that, of course, this allows you to rethink from the bottom up what is the detail, what are fibrous tectonics, what are the kind of systems that emerge from this radical dematerialization, and at the same time have this background dialogue. What is really the fundamental problem with the highly isotropic, homogeneous materials that we've built with in the 20th century? And we actually have unlearned how to deal with building with fibrous materials. Here I also have a small video. And I come to an end in a second. Okay, I will wrap up now. I think what is interesting is I think that sort of as a kind of side product of all these investigations, there's now a kind of company who does that. There's now a sort of new kind of building industry that uses this also as an alternative business model, and I think that means that we can now actually build with these systems. So this is actually a competition that we won for a new textile research center in the south of Germany. And here the fiber structure is primarily the envelope, that is the sun shading and the barrier for the balconies. So it's not yet, I would say, it's a structural facade, but it's not part of the building structure. But the key challenge, of course, is how do you make something happen in a completely risk-averse situation for a public building with a public land. So I think it was fantastic to see that this can happen in a kind of very short amount of time. Really preparing, I would say, the road to actually then go the next step and making this an integral part of the tectonic system of the system. So I think I think it shows that there's scope for also reinventing and the way how we think. I would say the building industry is configured, because honestly, I'm not sure whether with the existing building industry we'll ever get to a different way of building. I think we just have to build up a parallel one. Okay, of course, and I'm just wrapping up on that, carbon fibers are currently petrochemically based, so we are now looking into carbon fibers that are lignin based, or natural fibers to start off with, which you can see here, which are flux fibers, for example. They also have fibers, flux fibers. And by that, you reduce the global warming potential fivefold. Of course, you also have a lot less performance and a far more complex design and fabrication process. Because now, again, you have to integrate all the biological variability and all the inconsistencies that are inherent in a system that grows as the cellulosic structure of a plant. So I think this was very interesting for us to make this shift and then recognize there's actually a lot more intellectual effort to deal with these materials than with the carbon fiber, which is kind of nicely consistent, but also needs to be produced at 1200 degrees. So this grows at ambient temperature, just using solar energy. So the next step is, of course, to see how we can use the methods that we have to deal with these additional possibilities, to adapt them, which was the first time we did this for this pavilion in the Botanic Garden of Freiburg, where we realized we need to have a different approach, and now we have actually established a very in-depth fiber data object model that allows us in different domains to deal with and integrate those biological variabilities from sensor-driven fabrication all the way to alternative models of how you would actually engineer something like this. It's sort of the base for what we like to call a computation and co-design framework, which could then probably be step-by-step generalized. So even the robotic fabrication process doesn't work in the first instance because the fibers are too weak to take the process tension. So you really have to actually have a much higher level of sophistication in the sensor systems that actually drive and monitor the process tension in the system. And here you can see how that then ended up in this sort of lower resolution flux nets that are actually the load-bearing structure of the system, which I think begins to allude to sort of the kind of space of possibilities that is opened up if we engage, again, in a different manner here, with very seriously with the natural resources we have locally available That's why we're actually growing in Central Europe for 4,000 years now. And how that also opens up completely new spatial and experiential dimensions. With that, I would like to close. I need to thank the fantastic team of the Cluster of Excellence at the University of Stuttgart. Of course, this has not been done by me. This has been done by all these absolutely fantastic people that you see here. And I thought what is really important is to extend an invitation to you that we have an international research network that is very well presented in Central Europe, as you can see from the world map. A bit underrepresented in South America. It's completely free. So it's actually it's this kind of a network between a couple of large research centers in Germany, in Switzerland, in Denmark, also in Austria, in Australia. You can just register. We have around 1,000 members now. You can actually participate in all the network events. And we would love actually to have your perspective also being more present so that we can also, I think, engage in a dialogue, understanding, of course, how this very, I would say, locally specific way of how we approach things could be enriched also by understanding your ways of advancing architecture, engineering, construction. So if you want to just join on advancedac.net, I think what is really fantastic about it, it really allows individual networking. So if you sign up, there's a really nice database where you can find like-minded people across the globe, and that's how most of our researchers use it. Not to participate necessarily in events, but to actually find others that have similar interests. With that, sorry for being a bit too long. Thank you very much.